It is time to talk about nuclear half-life. We know that unstable isotopes, unstable nuclei decay, and there's nothing we can do about it. We cannot speed up this process, we cannot slow down this process, we cannot stop it. So nuclear half-life is our way to measure how quickly this process takes place. Nuclear half-life tells us how long it takes for nuclear process to occur. Here's our basic definition. Half-life is time required for half of a radioactive sample to decay. Let's look at this example. Here we have a thorium-234. It is unstable isotope of thorium that undergoes beta decay and turning itself into palladium-234. And let's say we have a big block of thorium-234, 80 grams of it. As the time goes by, thorium decays into palladium. So if we analyze the composition of this block 24 days later, we will see that out of 80 grams that this block continues to weigh, only 40 grams are made of thorium-234. The rest of it is made of palladium. Another 24 days go by and we have a block and we analyze it once again, and look at that, we only have 20 grams of thorium and the rest of it is palladium. 24 days later, only 10 grams of thorium left. This is happening because thorium continues to decay into palladium at a constant rate. And this period of time, 24 days, is the half-life of the thorium-234, the period of time that is needed for half of the sample to decay. So every 24 days, the amount of thorium is cut in half because through the process of beta decay, it turns itself into palladium-234. The half-life of this reaction is 24 days. And here is the symbol of half reaction. T, subscription 1/2, equals, in this case, 24 days. Here is a graphical representation of the same idea. The initial amount of thorium is decreasing. Every 24 days there is half of the initial sample that we have, and we see that the amount of thorium is decreasing. But this graph is a little bit misleading. It makes you believe that right in front of your eyes you would observe disintegration of the sample. Please do not forget that while thorium is decaying, it is decaying into palladium-234. So all this decrease in the amount of thorium will be compensated by the increase in the amount of palladium-234 in the sample. So nothing really visually be changing for us. Unless we analyze the composition of the block, we will not even know that it changed from one element to another. Yes, bunch of electrons, bunch of beta particles released along the way, but they are almost massless, so we will not even observe any kind of significant decrease in mass. Half-life of different isotopes can vary significantly. Let's look at these two examples. Okay, both of them undergo alpha decay. If we get ourselves a tiny sample of uranium-238, let's say 10 atoms, no more, to see 5 of them to decay into thorium, we will have to sit and wait for 4.5 billion years. But for polonium-218, it takes only 3 minutes. So this one is pretty quick. Half-lives of selected isotopes is given in your reference table N, and you can see that it can vary from days to years to milliseconds and to minutes and even billion of years. Let's look at some half-life sample problems. Here we have a radium that undergoes alpha decay and turns itself into radon. Half-life of this reaction is 11 days. So we have initial mass of the radium to be 120 grams. The question is how much of the radium will be left in the sample in 44 days. So we start with 120 grams, 11 days later it is 60, another 11 days go by and it will be 30, 15, and then the final 7.5. So the answer, 7.5 grams of radium will be left in the sample after 44 days. Initial mass of hydrogen-3, also known as tritium, is 80 grams. How much of tritium will be left in the sample in 61.55 years? Okay, if we check table N, we will see that the half-life of tritium of hydrogen-3 is 12.31 years. So let's figure out how many half-lives will fit into time period that is given to us. 61.55 divided by 12.31 equals 5. So the question is pretty much asking how many grams of hydrogen-3 will be left over after 5 half-lives. We start with 80 grams. One half-life later, it is 40 grams. Another half-life later, it's 20 grams. Then 10, then 5, and finally 2.5 grams. After 5 half-lives, there will be 2.5 grams of hydrogen-3 left in the sample. A quick check to make sure that we do have 5 half-lives in our calculation is to count all the arrows that represent half-lives. So 1, 2, 3, 4, 5. Sometimes you are asked to calculate not the final mass of the sample, but the final percent of the sample that will be left after a certain period of time of nuclear decay. So over here, we see that the question asks to find percent of the sample of hydrogen-3 that will be left after 61.55 years. Okay, we know that 61.55 years is a 5 half-lives. Because in the previous problem we already did the division, we know 61.55 years is 5 half-lives. So over here we are not even given the original mass of our sample of tritium because it's really not important. No matter what, how big or how small was the sample, the original amount will be considered to be 100%. Now we need to see how much, what percentage will be left over after 5 half-lives. So we start with 100%. One half-life later, 50%. Another half-life later, 25%. Then it is 12.5, then it is 6.25, and eventually we can see that 3.125% of the hydrogen-3 will be left over after 5 half-lives, after 61.55 years. Here's variation of the same problem. And here you are asked to calculate fraction of the sample of hydrogen-3 that will be left after 61.55 years. We already know that 61.55 years is a 5 half-lives, so pretty much what the question asks, what is the fraction of the original sample of tritium after 5 half-lives? Okay, so once again, we're not even given the original amount of hydrogen-3 because it's not important. Whatever it is, we assign it to be initially a 1. And then in 12.31 years, it will be 1/2 of it. Another half-life later, it will be 1/4. And another half-life later, it is 1/8. And then it is 1/16. And eventually we can see that after 5 half-lives, there will be 1/32 of the original amount left of the hydrogen-3. Let's see if we can handle this problem. Iodine-131 has a half-life of 8 days. And a patient consumes 10 milligrams of iodine-131, and we need to answer in how many days that amount will turn itself into 1/128th of the original amount that is given to us. Over here, this information about actual consumed milligrams of iodine-131 is actually destructor. We don't need to know original mass to figure out fractions. So whatever was original mass, we assign it to be 1 at the beginning, and in 8 days it will be 1/2 of it, and then it will be 1/4 of it, and 1/8, 1/16, 1/32, 1/64, and eventually we see that it is 1/128. So we know that every single arrow represents a half-life. And half-life of the iodine-131 is 8 days. So how many half-lives did we get? 1, 2, 3, 4, 5, 6, 7. So 7 times 8 it makes up 56 days. In 56 days, of the original amount that was consumed by the patient, only 1 over 128th of it will be left in the body. Here we have the same problem, but we are asked to calculate final mass of iodine 131 that is left in the organism after 56 days, aka after 7 half-lives. Well, over here, the information about the original mass is important. We start our calculations with that. So 10, 5, 2.5, and so on until we hit 0.078 milligrams. We can do the arrows, or we can do actually, since we know the fraction, we can calculate it faster by saying 10 milligrams over 128 gives us the same number, the final amount of iodine 131 left in the body after 56 days, after 7 half-lives. Okay, variations. Here we are asked to calculate percent of the iodine 131 left after 56 days, after 7 half-lives. So we can start with 100% because whatever is original mass is considered to be 100%, and we can do arrows. Or we can use our prior knowledge, our calculated final mass, and calculate what percent it is of the original mass. 0.078 over 10 grams original mass times 100% gives us the same number, 0.78%. Pause this video and solve these problems on your own. Now check your answers. There are 4 errors in all of my calculations because I know that 24 hours it is 4 half-lives, and there will be 0.625 grams of the original amount left, which is 6.25% of the original sample, and if we represent it as a fraction, it will be 1/16 of the original amount that was given. Last couple examples. Here we need to figure out the half-life of krypton 74 based on the fact that it took 34.5 minutes for the original sample to decrease to 1/8 of it. So first let's figure out how many half-lives it takes to get from 1 to 1/8. 1, 2, 3. So now we know that 34.5 minutes include in itself 3 half-lives. To figure out what is the length of a 1 half-life, we take 34.5 divided by 3. It is 11.5 minutes. So the half-life of krypton 74 is 11.5 minutes. And here we have unknown radioisotope. We know that to get from 200 grams to 25 grams, it took this radioisotope to decay for 11.46 days. So we need to figure out the half-life of this radioisotope. Let's see, how many half-lives does it take to get from 200 to 2500 to 25 grams. So 200, 1 half-life later it is 100, then it is 50, and then it's 25. So it is 3 half-lives. So there are 3 half-lives that fit into 11.46 days. So we take 11.46 divided by 3, and we know that this radioisotope has a half-life of 3.82 days.